So, beam steering in case of a phased array. What is our problem? This is the problem proposition. I have an array, I call this transducer element 0 just for symmetry purpose, right. Transducer 0 is the center element, transducer 1, 2, 3 are all on the one side, minus 1, minus 2, minus 3 are all on the other side, okay. And this is tau. I do not know with the resolution you are able to make out this is a tau and not t. Tau is a very generic variable that we always associate with a time delay, and therefore, so from what we saw already, each of the element can have its own time delay unit, right. So, you could have tau 0, tau 1, tau 2, tau 3 and so on corresponds to each of the transducer element. The transducer element itself has a dimension. So, you have a h is the width of your transducer, and d is the distance between center to center, center of the element to the center of the element, which is also called as a pitch, okay. So, this is an important jargon that you will, pitch is an important parameter when you choose a transducer and design of your beam forming, okay. So, pitch is d. What else do you have? This is your z direction, this is your x, that is the length direction of your transducer. So, you could have your transmit pulse can be given to each of the transducer elements separately with its own time delay. So, if you take a situation here where we are sending this plane wave in a particular direction theta, right. So, the plane wave is now travelling at an angle theta. So, we are interested in beam steering. So, we have taken an arbitrary angle theta, the direction in which you are now wanting to send your waves, your plane waves, right. You want it to go in that direction. So, how do we calculate? So, problem proposition is how do you calculate these tau values such that the waves will go in the direction theta, right. So, looking at it, what do you see? Let us assume that the speed of sound in the material is c, right. Let us not worry about any other value. So, this is an important aspect. Most of the scanners are calibrated with c, which is an average tissue value of 1540 meters per second, okay. If you are not given anything, you could assume it is 1540 meters per second. But the idea is my c in the medium is taken for granted now, right, okay. All I have control over the time because I am exciting it, right. So, which crystal, what time I am exciting, I have a control. So, if I want to do this, right, what should be the relationship between the delay values of the successive elements, or what pattern of excitation should I have for each of the transducer element, okay. So, looking at this, if speed is same, right, you want time, then you know the relationship between speed and time, you have to have some distance, right. So, look at this. So, if I want to this plane, right, this plane has to go like this. That means when I excite transducer T0, it sends out a wave. If I excite T1, that sends out a wave. If both of them have to be aligned, come along this line, the phase fronts have to form a line, right. Then the idea is what is the distance, right, what is the distance that is different, or the path length, right. We do not call it distance, we usually refer it to path length. Path is the path with the wave is taking, length is the length in the direction, path length that a wave takes from T0 to come here, and path length that this T1 from here it comes here, what is the difference, right. So, T1, this is the distance. So, if you take that, you have a T0, right. If you have to, T0 has to come here, the wave that is excited at T0 has to travel this extra path length, so that the wave from T1 and T0 fall in the line, right? They all arrive at the same time to form a line. So this is the extra distance, extra path that has to be travelled, so that you from T0, so if it has to travel this much, another way to look at it is, that means I will have to wait exciting T1, right? I have to transmit, use my T1, delay it until the wave that is excited at T0 comes this distance. Then I have to excite this, correct? So let us write it down. So let us write down the extra distance that T0 must travel than T1, that is this guy, right? This is the extra length this wave has to travel from T0. That is going to be what? Oh, you have your theta here, right? So you can quickly, and then you know the center to center distance, which is your d. So I know my d, I know my theta, so I can relate d. All I need to do is this extra length. What is that, right? That extra length delta d is d sine theta. Okay, so d sine theta. So if this is the extra distance that it has to travel, what is the time it takes to travel? You know the velocity c. So it is that to make the wave from T1, right, arrive at the same time as T0, it must be delayed by the time for this wave to go this much, right, delta d. So your delta t, the delay should be delta d by c, or d sine theta by c. Okay. So this is for T1, right, but the same logic I can have for all the others, T1, T2, T3, or T minus 1, T minus 2, T minus 3, all of them the logic is same. So if I excite this, I have to excite left even further, even before T0. The T minus 2 should be excited even before T minus 1. I have to excite each one of them slightly ahead, so that the angle of steer, so this it's all steering in this direction, correct? The left guy, the left element must be excited first than the second element. If you do the opposite case, you can steer it the other direction, right, minus theta. So point is, okay, this is fine. What do I do for any? So if T naught transmits at T equal to 0, Ti fires at, right, we can generalize that, Ti is I delta t. So your I d sine theta by c, clear? So this is your time delay. So you could actually think about, so if this is the main lobe, right, this you have accomplished steering, right? I want to, now I can change whichever direction depending on the theta. I can manipulate my excitations for each of the crystals, right? Each of this will be a separate channel. So you could do delay, corresponding delay you can code, and you can execute this. Very neat, right? Of course, the only challenge that you need to worry about is when you talk about direction of steering, we are always worried about grating lobe. What is grating lobe? Again, this is a very tricky concept, very powerful, important. It plays a lot. It kind of dictates some conditions for certain realization of arrays. So it is very powerful. But just to give you, so in a full course on ultrasound, I would typically go into full detail on this. But just for the purposes of introduction and not letting this word go without some 30-second intro, right, that will be kind of doing injustice. So what I will do is just make you think of an analogy, right, analogous situation. Maybe then it will be easier for you to appreciate what I mean by grating lobes. You know main lobe, right, main lobe and side lobe. just for the purposes, recall your antenna pattern, right? We said this is your main lobe and then your side lobes were like this, right? So it has to do with direction, for example. Now, if I want to steer, that means at some angle, that means I am going to have, this is rotated, right? This is going to be rotated. Let me just draw for the sake of right. That is going to be my angle. So now that is some theta. Okay. So the problem is, when you are trying to look at this direction in theta and you are trying to send the signal in theta direction, so whatever you are going to receive, right, you are going to think that it is coming only from theta direction. The problem with, of course, there is this small side lobes, but then we integrate over the side lobe, so we, it is just reducing the signal quality, but it's okay. I mean, it is a problem, but side lobe we know how to do apodization to minimize its effect. But grating lobe is a problem, because when I am looking at this direction, what if I have another cousin of this main lobe at another angle, right? If I have same pattern, side lobe, right? You have another, if I have another main lobe and side lobe, then, oh, I am actually thinking I am sending in this direction, but the wave is also going in this direction. If that is the case, now I am caught. I might be completely wrong, right? I might think that, so there is some target here, for example. I am thinking I am sending it steering by whatever theta, and whatever I am receiving, I am saying, oh, there is a big obstruction at this location. But it turns out that even though I sent my theta this direction, there was additional lobe which is called as a grating lobe that actually was in another angle, and the object was in that angle. So this reflection came, I have basically coded it wrong, right? I am registering this object to be here because of the grating lobe. So this could be a problem, but then you might wonder, why didn't we cover this in physics, right? Why didn't we cover this in the physics? Where is this suddenly coming from? We thought we were very careful in talking about wave equation, and we solved example wave, I mean example solution using your cosine theta, or right, a sinusoidal function. How did this get through? So challenge is here. When you do all of signal processing, we talk about analog first, right? So we have some signal, right? Some signal. What is the frequency spectra of the signal? Okay, you get something, right? This is your frequency spectra. Okay, and the first lecture that you do in digital signal processing is, oh, this is a continuous signal, it has its some spectra. First concept that you get to is, how do I sampling. When you do sampling, major concept is your Nyquist sampling criteria. Oh, now this is time signal. If I sample it, I have to sample it how fast? Oh, I have to sample it at least twice the highest frequency. Oh, if this is the spectra, right, I have some highest frequency, I will have to sample it at least twice that highest frequency. Then, right, this is continuous time spectra, FFT. Have you, after you do sampling, right, how do they explain aliasing? Oh, you have spectra, but now when you sample, the Fourier transform or the frequency domain is going to have copies of this, right? So, you want to sample so that, let me just for sake of clarity not draw here another spectra. Now, this is of the discrete samples. Your spectra is going to be right. This is at Nyquist. If you sample it much higher than the Nyquist, there will be separation, right? You can have 1.5. So, essentially you have copies of your spectra, right. So, when you undersample, when you go below the Nyquist, you will have overlap, and so we call high frequency masquerading as low frequency, right, all these textbook definitions. Practically what is happening? Practically you have replicas of the fundamental spectrum. When you sample it, you have to sample such that it is not going to overlap. Okay. So, this is what you know from your basic time based 1D digital signal processing. However, here what are we sampling, right? In imaging it is all about space. Now, imagine we have what we covered so far for main lobe, side lobe is just one transducer, right. We had a width, right. We had a width, and then let us not worry about elevation. So, there was some height. So, do not worry. So, if you look at the rectangular transducer that we put two beam pattern. So, let us just take the width, which is in our imaging plane, right. It is in our imaging plane. You take this width. So, this is your element that we had before. Now, this single piezoelectric crystal is spatially sampled, right. That means I have different crystals, each sampled. So, this is spatially sampled crystal, clear. So, instead of one crystal for which I know you get a pattern like main lobe and side lobe, now I have sampled it, I have picked, right, different spatial locations. So, I have one crystal here, another crystal here, another crystal here. So, I have samples, I have different crystals at different locations, right. So, I have made it from one continuous piece of crystal to multiple discrete crystals, each spatially at some spatial sampling, each located at some spatial location, right. So, what would you expect? Oh, if that is the case, I would expect I will have copies of my Fourier transform. Remember the far field of the beam pattern that we talked about, the far field was your Fourier transform of your aperture. So, now if I sample my aperture, what should I get in my beam pattern? Copies, right. So, if I sample very well, that is greater than your Nyquist, I should have this not overlap, right. I should have multiple copies, but the other copies should be small, right. So, in order to avoid this grating lobe, there is going to be a constraint on how well you sample. The sampling here, the parameter is D, right, how close the two elements are. How close the two elements are is going to dictate whether you are going to have copies of your main lobe and side lobe. This copy of main lobe and side lobe is called as your grating lobe. Okay. So, I will just leave it at that. You can have your own imaginations of what it is, but that is a very powerful design constraint. Okay. So, you can have your grating lobe, sine of grating lobe to be sine of theta plus or minus. D is not a surprise because it is the spatial sampling parameter, right. So, it has to come somewhere. Note, so I is your element location. Notice it is in terms of lambda. So, lambda by D. Why is this important? Because if this gives you your grating lobe, so this is I equal to 1 or 2 is your first grating lobe or second grating lobe. Okay. So, ideally what do you want? I do not want any grating lobe, at least I do not want any grating lobe in the imaging direction. If I have my transducer here, right, if I have my transducer this way, this is my imaging direction. So, I do not want, this is my body, my transducer is at the surface of the skin. So, at the least I do not want any grating lobe within the imaging region or the forward region, correct. So, if that is the case, I can eliminate grating lobe. How can I eliminate grating lobe? Oh, because this is sin theta. So, grating lobe will occur at theta g will be occurring at sin inverse of this quantity. So, you would want this quantity if it is greater than 1, right, you do not have grating lobe. How do you make that? Look at this guy. So, sin theta 0 is sin theta 0, but look at this guy. If I choose my d to be lambda by 2, then I can avoid all grating lobes. Now you understand why this array is called phased array. So, it turns out phased arrays are arrays such that the d is lambda by 2. Now you see the problem. Higher the frequency, I get better resolution, lower the lambda. So, you need to have spacing to be lambda by 2. So, you see the intricacy in if you are having a high frequency, high sampled aperture, right. Then you have to have the corresponding electronics so that each one can do. So, it quickly becomes very sophisticated. Nevertheless, this is in vogue, this is very popular, right. So, it has certain applications where you need to have no grating lobe, clear. So, we will stop the idea of grating lobe here. I guess you get the feel. So, you should be able to calculate one from the other. You should be able to calculate grating lobe angle if the position is not d, if the separation is not d, what happens, what when you change lambda, what happens, right. All this can be worked out. Okay. So, this is for beam steering. We need to also do focusing, right, that is our other big objective. So, how do we do focus? Take a point where you want to focus arbitrary, some xf comma yf, this is your imaging plane, xz is your imaging plane, you have your point. So, now the objective of focus is I want all the waves to come at the same time coherently at this location, right. So, same logic, you have different crystals, each one has its own time delay that you can control when you can excite them. So, now the calculation has to be again what is the extra path length that each one has to travel, right. So, clearly if you have to arrive at this point, the closest needs to travel the shortest, the farthest need to travel the largest distance, right. And so, the range from Ti, any location here, Id is any location, T1, T2, T3, T4, T minus 1, minus 2, any location Id is here, 0 is, it is at the 0, Z is, it is at the surface. To the focal point is what? You can calculate Ri as square root of Id minus xf square plus zf square, clear. So, this is the path length if you will, right, Ri from each of the transducer element to the focal point. However, what are we interested? We are interested in time delay between T1 and T2, T2 and T3 and so on and so forth, right. When should you excite each of the crystals? So, that means you have to have path length is one criteria. So, if you assume T naught transmits at T equal to 0, then Ti should fire. When should it fire? It should fire to compensate for this R0 minus Ri by C, the path length, the extra path length, right, that is your, and path length by C, distance by velocity is your time, clear. So, if I do, so I can generalize this. So, I can generalize Ti is equal to R naught is xf square plus square, you have your Ri by C. Clear? So, so far so good. So, this is what you need to do. Intuitively we know that the shortest distance will be delayed most. The element that has to that is farthest away should probably be excited earlier, right? That way they all can come at particular location at the same time. Okay. So, if you were to plot the time delay profiles, this is how it will be. For steering, it was a linear, whereas you see when it is focusing, it is a parabola. Okay, you had a x square term, right? So, the parabola. So, clearly you can do combine steering and focusing, which is how. So, you can do whichever. So, your time delay that you are doing, the only thing you have to take care is negative time delays are not realizable. So, you can always have a say you cannot t equal to 0 we said, you cannot physically realize, you have to have everything in positive delay. So, the most negative delay that you calculate, you have to give that as a bias to every term. Then you can get a physically realizable relative time delays. Okay. So, you can see that you can realize both steering and focusing by combining the time delays, right. Steering alone is only linear, the distance, right, linear with respect to each of the element, the time delays are just multiplied, right, delayed, whereas here that is not the case. Okay. So, this is for transmit. So, I know I have sent the wave in a direction I want with a focal with a specific focus, I have sent it. Now, what do you do? So, this is your transmit beam forming, if you will. What do I do now? Now, I need to do the same thing with respect to receiver. Okay. So, here I delayed and then transmitted. Now, I am going to get the echoes. Once I get the echoes, I should probably do similar thing, right. So, what we call as receive beam forming. So, you have the echoes are coming back, right. If you send a plane wave, the echoes are going to come back, and you could do this reverse of what you did already. So, here this is what is going to go to your ADC. So, each channel will have a corresponding analog to digital converter. So, you have this trace, transducer 1 has one signal, right, transducer 2. So, each one is receiving the signal. Straightforward, apply the delay, the earlier one this you got, you have to delay more until you get the last one, right. Same profile that you got for transmit, inverse of that, which one was delayed there most will be least delay here. You can get the thing, right, get your receive data. So, we will just do it for focusing as well. So, dynamic focusing. So, dynamic focusing, what is the same thing, take that same x of f. Now, only thing is now the arrows are pointed the other direction. So, if you pretend now after the transmit beam came, it hit this point object, right, at the focus, and it is now sending the waves back, right. So, there is going to be a wave component that is going to hit this transducer, it is going to hit this element, each one at different times because the path length is different. So, straightforward we write similar to what we did. First consider a point x comma f. This wave will reach any element Ti at Ti your x square plus z square plus the extra path length, right, divided by c. So, if you care, this is very similar to, this is actually same as your transmit, with only thing is here we put a plus, there it was a minus, okay, or the same two components are there, right. So, you have your Ti, then what is the point? Oh, I know my time arrival, what is of interest? Time delay is of interest, right. So, I can time delay between the arrivals at T0 and at Ti, right, T0 and Ti, any location. So we call this as focused beamforming, conventional because most of the scanners employ this methodology. So here is a linear transducer, array elements labeled 1, 2, 3 up to n. This is your image. This is the ideal object that you want to image. What do we do here? We excite few crystals. I know how to do this, right? Focus. Elements are exactly the time delay calculation that you did for your phased array, just that the theta is 0 here, right? So you can excite with the delay value that is computed so that you get focusing at the center of this aperture, what we call as active aperture. What happens when you send it like this? You get echoes back. Once you get echoes back, all the echoes are hitting all of the active transducer elements. You get time trace, right? This is what this is the A signal that we got, AMO, amplitude. So each crystal now picks. So the advantage of using array transducer is I have each of these as a separate channel. So now what can I do? Oh, I will go do my beamforming. What do I mean by beamforming? I will employ the time delay. I just calculated the time delay for, right, receive beamforming. Same thing I can apply here. So each one will be, right, delayed depending on which location they are. I will do beamforming, delay, essentially delay compensation, apodization, right? I can do by apodization, just waiting each of it. It's a window function, right? So I can do apodization and then sum them. So this is a typical DAS, is a typical beamformer that is there in majority 90-95% of your scanners, ultrasound scanners employ DAS beamformer, delay compensation, apodization, summation. Do that, you get one line which is aligned to the center of the active aperture. Now what do? I need to scan from, this is just one A line. If you had a single transducer element, this is exactly what we got. This all happened, we didn't have control. Anything that falls on the surface were summed and what you received was only one line. Here we are doing it explicitly, only thing is we are able to compensate for the time delay because each one has a control, separate control. I have one A line trace, this is called as post beamformed A line. Okay. So I have only one line, how do I get an image? I do repeat the process. Now I will translate, right, 2 to n plus 1, do the same process, get the next line. So this is my scanning. I am not moving physically, right, but my electronics is translating the active aperture. So this is electronic translation. So electronic steering, if you want to call it, right. Mechanically we are not doing it. So you can do this so on and so forth till you reach the end. So now you get the image data, beamformed image data. This is the depth direction, this is your width direction. What do? Oh, this is raw data. What am I interested in image? It's a brightness image. So I need envelope and then color code, right. So I will do envelope detection, log compression, just so that you can see, few strong points do not saturate the image. So we do log compression, envelope detection, log compression. If you do, magic, this is the image that you get just by this operation, right. So this is the ground truth image, this is your ultrasound image, B mode image, brightness, sonogram, whichever you have heard it. So notice more or less the structure is there, but it has its own, so the resolution, you can see that it's becoming difficult to see here. This round is now not really round because deliberately it was stopped in the end. Okay. So if you use a much more sophisticated signal processing, do other things, we could improve the image quality further. But the idea is, now you are visualizing hopefully how we start with the physics, have instrumentation, how do we manipulate the instrumentation in the digital beamformer case to get a image. Okay. So will I hope this gives you kind of a good picture of what the big overview. A lot of details, it's a separate course in itself. I don't want to drag this further, but I think we have covered enough that you get if you look at this particular value, I hope you will be able to know, oh, this is the reflectivity that he was talking. Inside here there is no scatterers, so there is no reflection that is coming. So that is this point. Here you have high scattering region, so that comes as white. So the impedance mismatch, right, that is distributed. There is no scatterers here, so there is no impedance mismatch here, so there is no echo coming from here. Here is a huge impedance mismatch, and therefore strong echoes come from here. So you can now probably, and then look at this black and white texture that you see, that is your speckle. Okay, so I think you hopefully get a hang of how this is. Now this is straightforward. This you can now do it at steering angle, you can curvilinear, you can do the same methodology, right? You can get the image. So all other things, if you understand this idea of how to calculate the time delay profile and keep in mind the wave propagation, how it is happening, then you can actually jump into putting all the pieces together and form an image. Okay. So last part that just for the sake of completion I want to highlight is the Doppler principle. So from an image point of view, we covered what we wanted to cover, but the extra functionality we talked about Doppler, we are not going to cover. Doppler signal processing itself is a whole chapter in itself. Here we won't do it. So we covered the physics, so I will just show you the output, how it is typically used. So you know how this gray image is formed, right, your B mode image. So after you see a B mode image, you know where all, right, some flow is going to be. So what you see here is what is a duplex image. Wherever there is velocity, the velocity using Doppler principle is calculated, color coded, and it is overlaid on the B mode. So you can see the color bar is centimeters per second. Again, like I said, if it is flowing towards the transducer, it is one color, flowing away from the transducer is another color. So what you also see is there is a that is called as a range. Range is, right, range is distance, gate means range gate. So within this range gate, that whatever is the FD, remember we calculated FD, frequency shift, Doppler shifted frequency. So your Doppler frequency, right, this is plotted here, FD, within this small window in this range gate, because there is flow. If you take the data or the radio frequency data, right, that we call the echo data, only from this region, and see how with time the frequency is shifting, right, the Doppler shifted frequency. If you plot that, this is what it is. Okay. So this is the velocity from your Doppler shifter. So what we use here is your pulse wave Doppler, because we are using pulse echo. So it's pulse wave Doppler velocity display with a color flow image insert. So this is usually the color flow image they call. So the concept of Doppler is there. You fuse that with the challenges of scanning, right, and registering it with B mode. You can in principle get this color flow imaging. So you can see where is the flow, how much is the flow, which direction is the flow. Pretty neat, right? So but we will not cover, I mean that is going far beyond the scope of this introductory material. So we will stop here. I think we did justice to the modality, because this is just touching, trying to give you a big picture overview. At the same time, make sure some elementary concepts you are aware of. So physics we covered, reflection coefficient, right, your medium, Snell's law, those things should come to your mind. Speed of sound, material is needed for sound to propagate, unlike your electromagnetic waves, right. So your lambda is an important parameter, the length, wave number. So these are some physics that we covered, and then we talked about instrumentation, but primarily we focus on the transducer, right, transducer, backing material, but predominantly it was going to be with the resonant frequency, crystal size and shape, and beam pattern. So, beam pattern, transducer shaping, right, that is something that we covered. And then we came up with imaging. We covered 4 different modes: A mode, B mode, M mode, and we covered 3. There are other modes as well. C mode, like how you did computed tomography. Same thing can be done with ultrasound, right? You can have one transducer on one side, you can have another transducer on the other side through transmission. We have not covered that, but most popular among them is your B mode and combination with your M mode and Doppler. Okay, so that's what we covered. So take home message for the last part is your beam forming time delay profile. How do you design the time delay to accomplish focusing and steering, and the idea of apodization, incorporating apodization and doing this focusing also dynamic receive focusing. I think if you get a hang of this, this is a good point to stop the introductory material. If you are really excited, if you are happening to work in the area of ultrasound, perhaps you will find a future course in ultrasound dedicated to ultrasound lecture, ultrasound imaging alone. I recommend you to read that further or take that course in the future. So, for now, for the purposes of medical imaging system, we complete this module of ultrasound right here. Thank you.